More about natural deduction. We learned the rules for universal quantification. Now come rules for the existential quantifier. And that finishes the set of rules for natural deduction in predicate logic. The elimination and introduction rules for the existential quantifier are: exist introduction rule. From a t/x we can conclude exists x a, and there's a restriction. T has to be free for x in a. So this is the exists introduction rule. The exists elimination rule says that if we assume exists xa and we have a derivation of b from a as a temporary assumption, then we can conclude b and eliminate the temporary assumption a. The restriction here is x should not occur free neither in b nor in any uneliminated assumption in the deduction of b except perhaps in a. Let us discuss the motivation of these rules. Let us take a very informal example of the elimination rule for the existential quantifier. Assume that somebody likes jazz, and in addition, let us take it as given that everybody who likes jazz likes music. Now, since we assume somebody likes jazz, we denote by x that person who is assumed to exist who likes jazz. We denote that person by x. So we make a temporary assumption x likes jazz. When we combine this with the assumption that everybody who likes jazz likes music, we can conclude that x likes music. And now, since x likes music, of course, we can conclude that somebody likes music. So this is the conclusion: somebody likes music. Let us see what happened to x in this inference. X is not free in the conclusion somebody likes music. X has somehow disappeared completely. X only occurred in the temporary assumption that X likes jazz, and this temporary assumption was eliminated. Indeed, since we assumed that X was this somebody who likes jazz, we know nothing else about X. We only know that X likes jazz. We don't know anything else about it. So we shouldn't use or try to use any other knowledge about X because we simply don't know. And the assumption everyone who likes jazz likes music says nothing about X. X may occur there as a bound variable, but X does not occur there free. Let us now discuss the motivation of the exists elimination rule and the exists introduction rule. The motivation for the exists elimination rule is the following contemplation. The intuitive meaning of exists xa is that some object A in the universe of the model satisfies A when used as a value for x. On the other hand, we can derive B, which does not mention x at all, from the assumption A. So B is true whatever the value of x is as long as A is true. Well, A is true for the value A of x, therefore B is true. More exactly, suppose S satisfies there exists xa, and the assumptions used in the derivation of B from A. We argue that S must satisfy B. There is an A such that SA/x satisfies A, hence SA/x satisfies all the assumptions used in the derivation of B from A. Hence SA/x satisfies B. Remember that x is not free in B. So, since SA/x satisfies B, also S does. The motivation for the exists introduction rule is the following. We know a t/x. So we know at least one value of x that satisfies a, namely the value of the term t. Therefore we are justified in concluding there exists xa. More exactly, if S satisfies a t/x in M, then by the substitution lemma S a/x satisfies a in M for a equal to the value of t in M under the assignment S. In particular, S satisfies there exists xa in M. Why are we making those restrictions in these rules? Without the restriction in the rule exists elimination, we would get the following wrong deduction. We assume exists x p0x, then in order to use the exist elimination rule we make the assumption, the temporary assumption p0x. Okay, from this we can conclude p0x because from p0x, p0x, the conclusion and the hypothesis are the same. Now, if the exist elimination rule was available without